Hello guys, welcome again to our PIC assembly language programming tutorials with Devang Paddy. On this video, we'll be looking at the 2x16 LCD display and how you can interface it to your PIC microcontroller using assembly language. Right. Now, for you to be able to interface anything to your microcontroller, you first need to find out how that particular device or component work, what kind of information it accepts or gives out, and then how can you connect it and interface it to your microcontroller. So let's do that with the LCD. Looking at the LCD, it has 16 pins. First two pins being for supply, pin 1 ground, pin 2 VCC, right? And now the third pin is your contrast control pin. You will normally connect either a potentiometer here so that you can vary your contrast of the LCD, or you can connect a fixed resistor between VEE and ground to set a fixed contrast of the LCD, right? Now the RS line, the register select pin, which is pin 4, it is for selecting whether you are sending data to the LCD or you are sending an instruction to the LCD, right? So when this pin is high, you are sending data to the LCD. You want to write data to the LCD. When this RS line, when it's low, you are sending an instruction, a control to the LCD. So this pin, you will connect it to your microcontroller, and then through the program, you will tell the LCD whether you're sending an instruction to it or you're sending data to be displayed. That's the RS line. And now the RW line, the read or write line. The read or write line is for either you are reading data on the LCD or the status of the LCD, or you are writing to the LCD. Remember, you can write either an instruction or data, but when you read, you want to read what is on the LCD or the status of the LCD. So the RW, it is for either you read or you write. So when you write data to the LCD, the RW must be 0, must be logic 0 if you want to write. If you want to read, this RW must be logic 1, right? So you can either connect this RW to an IO to decide whether you are reading or writing. But if in your application you will always be writing to the LCD, you can connect this RW directly to ground, enabling write only. Right. Now, the E line, pin 6 of your LCD, it is the enable line. It is clock. Actually, you are clocking the data you are sending to the LCD. The data being data 0 up to data line 7. So you will send data. The data that you want to send to the LCD will be on these data lines, and then you will clock that data. And now the register select will tell the LCD whether the data you are sending, is it an instruction or is it data to be displayed on the LCD. So the RS will tell if this data is an instruction or it is data to be displayed, and you clock that data or you send that data using the E line, right? And that is if you are writing, right? But now if the read line, if this pin is high, it means whatever you are reading will be represented on these data lines to your microcontroller. When the read or write is low, you will be writing to the LCD display, right? Pin 15 and 16 are for LCD backlight, whether you want to switch on the backlight of your LCD. Pin 15 is supply for the LED backlight. Pin 16 is ground for that LED backlight. In some applications, the backlight is always on, so it means it's constant supply on V on pin 15 and ground on pin 16. In some applications, the backlight is not really important, so these pins are left unconnected. Or even in other applications, they will control the backlight through a transistor to switch on and off the backlight of the LCD, right? But in this tutorial, I'm not going to consider, or I'm not going to use the backlight of the LCD. Now, what type of data can you send to this LCD? This LCD accepts data in a form of 8 data lines, parallel communication. When you are sending this data all in 8 bits, and this is called 8-bit mode if you're using all 8 bits of this LCD. So we're going to do both 8-bit mode and the 4-bit mode. So let's start first with 8-bit mode. Now in 8-bit mode, we are sending 8-bit data to the LCD. So you send the 8-bit data to the LCD, and then the RS will tell the LCD if that is data to be written or an instruction sent to the LCD. And then the read or write most probably will be writing if we are sending to the LCD, right? So the read or write will be logic 0 to tell that we are writing to the LCD. And now once all of that are set, you clock your data, meaning you set a pulse through the E line. Through E line, it's clocked, so you're sending a pulse, a logic high pulse, so you switch your enable high for a small amount of time and back down. And then that clock will send this data to your LCD. But now, let's look then at what kind of data or what data are we then sending, depending on whether we have selected the data to be either an instruction to the LCD or the actual data which we want to write to the LCD. Assuming that we will be writing. I'm not going to do any reading on this video, so I'm going to assume, or I'm going to decide now, our read or write line will always be connected to ground to indicate that we will always be writing to the LCD. Now, whether we write a data or we send an instruction, that will be determined by the RS line, right? And then we use the data line together with the E line to send that information to the LCD after selecting whether that is data or instruction. Now, let's look at instructions first. What type of instructions does this LCD accept? Looking at this table, there are a number of instructions, but in this table summarizes most important instructions. Let's say you want to send a clear display instruction. The 8 data lines must have, you see, from D7 to D0. That is 00000001. When you send that 1 to your display through D7 to D0, and then your read or write, it is logic 0. Your RS, it is logic 0 to indicate that you are sending an instruction. This indicating that you are writing to the display, and then you are sending an instruction that says clear the display. So 01 in hexadecimal, 01 will be clear display. That's how we can send a clear display instruction. Right. Now, other instructions we can do, it's either we want the cursor on or off, whether we want the display on or off. We're going to discuss these instructions as we do an example on the program. Let's look at enable display and cursor instruction, which we can set. So the first 5 lines, the first 4 lines are 0 and D3 is 1. The 3 bits D2, D1 and D0 depend on what is that you want to do to the display. So let's look at what can we do with those remaining bits. If we look at D, you see here, if D is 1, we say turn on the display. If D is 0, if D is 1, we say turn on the display. If D is 0, we say turn off the display. Right. So that will be 1 if you want to send, if you want to turn on the display. So this will be for our data lines 0000, 1, 1 to turn on the display. And now the cursor, if you want to turn the cursor off, this will be 0. If you want to turn the cursor on, that will be 1. Now to blink the cursor, if you want the cursor to blink, this will be 1. If you don't want the cursor to blink, that will be 0. And then if, let's assume that you want to turn off the cursor and you don't want the cursor to blink, I mean this will be 0, 0, but you want the display on, this will be 1. So this will be 0, 0, 0, 0, 1, 1, 0, 0. 0C in hexadecimal. When you send it to your display, it will switch the display on, turn off the cursor, and then turn off the blinking of the cursor. So these are basic instructions. If you want to find out more on what type of instructions, just Google LCD interfacing using HD 44780 Hitachi chipset. You will get this data sheet. Right. Let's just now look at how we will send data to the LCD. Sending data to the LCD, the RS line must be 1. And we are still writing. The read, write will be 0. Because we are still writing to the display. And now we can send whatever data we want to send to the display. Now, let's say maybe you want to display a character on the display. If you want to display a character, the data that you send here will represent that character you want to send to your LCD display, right? So what type of data, or how will you know which data represents which character? Let's look at this table here. This is the ASCII table for all characters that you can send to your LCD display, right? And looking at this character, if you send this, the 8-bit value for the characters, bit 7 to bit 4 being on this side, and then bit 0 to bit 3 being on that side. So if we send 3, 0, will be displaying 0. If we send 3, 1, will be displaying character 1. If we send 3, 2, we will be displaying character 2. Right. And then if we send, say, maybe 5, 0, we will be sending an uppercase P, and so on. So this is the ASCII table for the characters you can send to your LCD display. So these values 3, 0, 3, 1, 3, 2, or 5, 0, 5, 1, whatever you want to display. This is the data which you will send to your LCD display through the data lines to display that particular character. Right. Now, when we send data to the display, remember the read or write line must be 0, and now the RS line must be 1. We are sending data. But if the read or write is 0 and then the RS line is 0, we are sending instructions. When the read or write is 1, it is when we are reading. So it is either we are reading the flag, the status of the display, whether it is busy or not, or whether we are reading the character sent to the display at a particular location of that display, right? So I said we are not going to use the read, so we will connect this RW always to ground to indicate that we will always be writing to the display. Either we will be writing data to the display or we will be sending instructions to the display. RW will be 0 all the time. Right. Now, let's see now how will you connect your LCD to your PIC microcontroller in 8-bit mode. Right. Using 8-bit mode, let's see now how are you going to connect your LCD. This is typically what we are going to do, or what you have to do, which is what I'm going to show you now in this tutorial. In 8-bit mode, all 8 data lines of the LCD are used and connected to your PIC microcontroller. So in this case, I've connected data line 0 of the LCD to B0, port B0 of the microcontroller, up to data line 7 to B7. I said I'm always going to send data to the LCD. I'm not going to read from the LCD. So the read or write is constantly connected to ground, right? And then the E line is for clocking the data. The E line, I've connected it to A1, and the RS line, where I'm sending an instruction, a control, or I'm sending data to the LCD, that is decided by A0. It's connected on A0. Now, VSS and VDD connected, and now your contrast connected through a 10K control to modify your contrast. I said you can either connect a potentiometer or you can connect a fixed resistor between VEE and ground. Right. Now, in this example, the backlight is always on, pin 15 connected to VDD, and pin 16 connected to ground. Right. So now, this is a typical connection for your 2x16 LCD in 8-bit mode. Right, in 8-bit mode. Now, because an LCD has a processor in it, when we send information, there's a processor that receives that information and relays it to the LCD. So we need to give it time to do that processing. So whenever I send information to the LCD, I'm going to wait 2 milliseconds maximum to give it time, because I don't want to read if it is still busy or not, because the read or write is connected to ground, meaning I'm always going to write, I'm not going to read if it is busy or not. And every time I send information to it, I'm always going to give it a 2 milliseconds time to process the information. That will be more than enough for it to process and finish whatever I'm sending to it before I can send in the next information, right? Whether that's being a control or being data, it doesn't really matter. Now, another thing to notice of importance is that because there's a processor in there, we need to initialize that processor. We need to tell that processor that we are using this LCD in 8-bit mode, because this LCD can be used either in 8-bit mode or in 4-bit mode. Now, the 8-bit mode, it means we are sending all data, we are using all data lines to send our information. Right? In 4-bit mode, it means we are using only 4 data lines, and we will discuss the 4-bit mode later on in the video. But now in 8-bit mode, we are using all 8 data lines, and then we need to inform the LCD that we are configuring, or we are using it in 8-bit mode. Right? I will show you as we read the program how do you initialize your LCD, and then later on we'll also do the same for a 4-bit mode. Right? So now that we have our hardware and a little bit of understanding in terms of the pin out and the function of those pins, let's try and write an assembly program for this LCD to display some information on it. Right? Now, before you can write a program, any program, first you need an indication of how are you going to approach this program writing process. So let's start off with a flowchart. Let's start off with you doing a flowchart for your LCD. Right now, for a flowchart, let me then use Paint to do our flowchart. Flowchart always starts with your power on or start, as we discussed in previous videos. So it says start there. Now, from start, what is it that we want to do? We want to go and initialize our microcontroller. Right. Now, how are we going to set up our microcontroller? How are we going to initialize this PIC microcontroller? Because we have connected now our LCD in 8-bit mode, we have the whole of port B connected to the LCD, sending information to the LCD, because I said we'll always be writing, we won't be reading. So port B is going to be outputs sending information to the LCD. And so is port A0 and A1. They are going to be outputs also, setting whether we are writing data or sending instructions, and then A1 sending a clock signal to send data to the LCD. Right? So all of these pins are going to be outputs. So we need to go and initialize our microcontroller and set it up in such a way that these pins are configured as outputs. Right. So let's do that and show it on our flowchart. So we say here, we make all port B pins outputs, right? Let's make all port B pins outputs. Right, on port A, we also need A0 and A1 to be outputs, but we're not gonna make use of any inputs in this program. So we can also make all port B or port A pins, all of them, although we are only going to use A0 and A1. Let's also make all port A pins outputs. Right. Now, I said when you send information to the display, you need to give it time to process the information you've sent to it. Right. And I said we're going to wait 2 milliseconds for that purpose. Whenever we send information, we wait 2 milliseconds, and then we can send the next information, wait 2 milliseconds, and next information 2 milliseconds. So I'm going to use timer 0 for my delays. Basically, setting up timer 0 in the PIC 16 microcontroller, it's just a matter of configuring your option register, setting the prescaler, knowing the frequency of your oscillator, and using your timer 0 in timer mode. For that, you will need to refer to the timer 0 video which we did earlier on. So basically, these are the only 3 things I'm going to do at initialize. Make all the pins outputs, and then set up our timer 0, which I'm going to use for delays, right? So basically, and then let's assume that in this application, I'll be using the PIC 16F84A, right? But if you're using another version of a PIC microcontroller, you might want to either disable analogs before you can make use of certain pins. But for the 84A, there's no trouble of displaying or disabling any of those. For this application, I don't need to disable anything there because 16F84A doesn't have too many modules in it. Now, after configuring my pins and setting up for timer 0 delays, I now need to initialize the LCD display, because I said that LCD display has a processor in it, and then we need to tell it whether we are using this display in 4-bit mode or 8-bit mode, and basic things we want to set it or we want it to do. We need to initialize it. We need to tell it before we can make use of it. So I'm going to say here, initialize the LCD display. Now here I mean we'll be using 8-bit mode to start with. That's the most important thing I need to inform this display for this particular example. Right. I can go further and say inform it to increment the cursor every time I write a character, increment cursor. Every time you write a character, it goes to the next address so that it doesn't write on the very same address all the time. So, but on default, I know that the LCD does that, but I'm just putting it in and I'm going to set it up as well, just to make sure that that is the case, right? So you initialize the LCD by informing the processor that you will be using this LCD in 8-bit mode. Tell it to increment the cursor. I can go further and say display on, cursor off, and then cursor blinking off, as we have seen on the data sheet. Those are the things you have to do at initialize. You can always modify them in the program at any time, but you first at least need to inform it at the beginning that you are using the LCD in 4-bit mode. Then, after initializing the LCD, you can start sending information to the LCD. Let's say now, here we will start writing to the LCD. We will decide at that point what is it that we want to write to the LCD. So writing to the LCD includes sending instructions and data to the LCD. For example, if you want to start writing from the top right corner of the LCD, you need to tell it, start writing from this particular address, and because it's going to increment automatically, you just need to tell it, start writing from here, and then when you send data, it's going to start writing and displaying that data as you send it. Or if you want to write on the second line of the LCD, that is an instruction. You need to say, jump to the second line of the LCD at this particular location, start writing from there. So the writing to the LCD includes sending data and instructions to the LCD. So we're going to start writing to the LCD now. And we will decide then what is it that we want to send to this LCD, right? So basically those are the steps. These are the steps that we need to take for writing our program. Now, one other important thing which I left out, which I may include, I think is very important. So if you don't do it, most probably your LCD will never work and you will wonder why. There's a block here. Now, whenever you switch on your system, whenever you switch on your circuit, because there's a processor on the LCD, that processor starts initializing the display itself, starts communicating to the display and setting it up before you can send information to it. It has to initialize itself. So you need to wait for it. They say you wait for it to warm up. Wait for the LCD to warm up, not in terms of temperature, right? Wait for the LCD to set itself up, and then the recommended time to wait here is 1 second. Wait 1 second. At power on at the beginning, just wait 1 second before you start sending any instructions to the LCD. Wait for the LCD to warm up. Right, so we're going to do that. We're going to create a delay where we wait 1 second before we initialize our LCD, right? So let's connect these blocks. And then in here, it will depend what we do, whether we have the next block or we are stuck in that block, right? So this is basically how we're going to approach this program writing for the LCD. Right now, let's go to our MPLAB. For this video, I'll be using MPLAB X or MPLAB 10. And then we will create our video or our project. Go to File, New Project. A standalone microchip embedded project. Next. Now you choose a device here. I'm going to type PIC 16F84A, or even the 84 is fine. Next, I'm using the PIC kit programmer. Next, assembly language. So the tool suite there to be MPASM. Next, you give the project a name and then you can browse. So I don't need to browse. I'm going to save this project under examples on the desktop. So I'm just going to give it a name, say LCD example. And then click finish. Right? Project is created there for you. We need to add a source file to this project. It doesn't have any source file. Remember, source files where we'll be writing our project. So I'm going to say new PIC 8-bit sample ASM, give it a name. I can give it the same name as my project name, LCD example. Finish. That program will be, that source file will be added there with .asm extension and with an initial code to start with. I want to start my own program, so I'm going to erase all of it. Now, things that you should know by now. We set at the margin, we have labels. So a semicolon denotes a comment. We have labels at the margin. And then we have instructions. We have operands. And then we have comments. Easiest way you can arrange your program. So the first two instructions, list P equals to 16F84A. Here we are actually informing the compiler that we are using the PIC 16F84A processor or microcontroller. Right? Now, this one, hashtag include P16F84A.inc. We're saying here, include in this project that file, or we want to make use of the file in this program. I did clarify on previous video what is the significance of this file and what it includes in it. I'm not going to do that. We are just saying there, include this file in this project or in this program so that we can use its contents. And now we can have our origin OX00, which is our reset vector. And now at 00, we want to go to initialize or start. We need, let's go to initialize, right? And then initialize becomes our label. So if we say let's go to initialize, then we copy this initialize, and then it's going to be our label somewhere. Let me put it there. Now, going back now at initialize, what is it that we want to do? At initialize, we want to set up our microcontroller. We want to make all port B pins outputs, all port A pins outputs, and set up our timer 0 so that we can use it for delays. Right. Now, in this example, let us assume that I'll be using my timer 0 in timer mode, and we'll be using a 4 megahertz crystal oscillator for our application. Right. So I'm going to perform calculations for timer 0 based on a 4 megahertz crystal oscillator and using timer 0 in timer mode. I'm not going to do those calculations in this video. There is a video I did on timer zeros. If you need to refresh your mind about that, you can refer to that video. I'm just going to make use of the values I know that will make up the 2 milliseconds. I need the 2 milliseconds delay. I'm going to do that using timer 0. I also need a 1 second delay just before I start communicating with the LCD. I'm also going to do that with timer 0. But you can use other methods to create your delays. You can use loop delays, use instructions to generate delays, knowing the speed of your oscillator, and then you can create a loop delay for 1 second. You can also create a loop delay for 2 milliseconds. Right. Now, what we want to do at initialize, from reset vector, we go to here, and then we want all port B pins to be outputs, all port A pins to be outputs, and then I want to set up my option register, because in the PIC 16F84A, the option register is the one you set up for your timer 0. Right. So those are the 3 things I need to do: port A, port B, and the option register. So let's go back to our program. Now, to set up port A and port B as outputs, I need to access the trace registers, which are in bank 1. So I'm going to switch to bank 1 by saying bit set file status, RP0. This takes me to bank 1. Switch to bank 1. Now that I'm in bank 1, I want to make all port A and port B pins outputs. Clear file. It doesn't matter which one you start with, but according to the flowchart, I started with port A, so let me just do trace B. I started with port B, so let me do trace B first. Then I went to port A, so let me say clear file trace A. So I've made all port B pins outputs, and now I'm making also all port A pins outputs. Make all port B pins outputs. Do the same for port A. Make all port A pins outputs. Right. Now, for my timer 0, I'm going to move now. Here I'm setting timer 0 prescaler to 1:256, right? Now timer 0 in timer mode. Right, and the clock source is from F oscillator divided by 4. Right. That's what that whole value sent to option register does. Right. Now I've done those three things. Now I want to now wait for 1 second. I want to now come and wait for 1 second. After I've set up all of these, I want to come and wait for 1 second before I start communicating with the LCD. Right. Now, for me to wait that 1 second, I need to call, or I need to create a delay routine that will wait 1 second. Right. I will want to do that when I'm in bank 0. So let me just, while I'm here, switch back to bank 0. Be clear file, status, RP0. Because I've done with initializing, I can switch back to bank 0. Switch to bank 0. Now that I'm in bank 0, let me just do that by saying call. I'm going to call my 1 second delay a second, or SEC, just a sec. So call sec. What will happen at sec? You will wait 1 second, right? And then after waiting that 1 second, I'm going to write this routine. For now, don't worry about what that is. This is a subroutine which I have to state what goes into it. Or let me just do that now. So let me put my 1 second between initialize and go to the, and say, okay, this, I'm going to put it in here. And then here will come a bunch of code that will wait 1 second. And then after that 1 second, I return from the call. So when I call 1 second, the program jumps to here. It processes the program that is here. After processing all of that, the time it returns, that will be exactly 1 second. Right, I will have waited 1 second before I return, and when I return, I will start communicating with the LCD. So let me actually do that 1 second routine. C block, I'm gonna need a general purpose register. Hence I'm doing C block, starting from, okay, C block basically says start defining general purpose registers starting at memory address that you have defined there. So start labeling, or start equating temporary registers. So I'll call this one temporary register. I just need one for now. So there's a temporary register which is a general purpose register at address 20 in hexadecimal. If I have another register here, let's say I have another register and I call it count. Count will be a general purpose register at 21, and then they will increment as I add more registers there. So for my 1 second delay, don't ask me where I get this number from, because I've performed my timer 0 calculations. So I'm moving a hexadecimal 10 into temp, right? My timer 0 is already running. So let me start by clearing it, starting from 0. Clear file, TMR0 register, right? Start from 0. And now I'm going to say, let's say an outer loop, or an out loop, right? So bit clear file, I'll say int con timer 0 interrupt flag, clear timer 0 interrupt flag. And now the inside loop, the bit test file skip if set int on timer 0 interrupt flag. And then if that flag is not set, you don't skip. Where do you go? You keep on checking if it is set. In loop, go back checking if it is set. If it is set, decrement file, skip if the file is 0. Which file? Temp, save the results into file. If temp is not 0, go to out loop and add out loop, clear the timer 0 interrupt flag and wait for it to be set again. And then whenever you get an interrupt, you skip, you decrement temp up until temp gets to 0, meaning you move 16 into temp and you have to get 16 interrupts for temp to become 0. And on the 16th or on the 60th interrupt, when temp becomes 0, it skips and it returns. So basically here, you load 16 into temp and you start your timer 0 from 0. And now, based on the calculations I've done, which I also did on the timer 0 example I did, if you have 16 interrupts, if you have 16 timer 0 interrupts, and then your processor is running at 4 megahertz with your prescaler set to 1:256, 16 of those interrupts, they give you 1 second, roughly, right? Without having to load an offset here. I don't want to load an offset. So I load 16 into temp. That 10 in hexadecimal, it is 16 in decimal. So I load 16 into temp, start my timer 0 from 0, and then I clear the interrupt flag. Right. So timer 0 is counting from 0. Remember, it overflows at 256, meaning starting from 0, when it overflows, this bit will be set. So I clear it first and then I clear the bit and wait for that bit to be set. So bit test file skip if set. When that bit is set, timer 0 has overflow. That is the first interrupt. Now, when this bit is set, I'm going to skip. But as long as this bit is not set, I keep on waiting for this bit to be set. Once that bit is set, that will be my first interrupt. I skip and I decrement temp. Temp had 16. If you decrement it for the first time, it's going to have 15. The results are not 0, so you're not going to skip because this one says decrement file, which is temp, skip the next instruction if the results are 0. But then the results are not 0, so you're not going to skip. What are you going to do? You're going to go back to out loop. And at out loop, you clear this interrupt. You wait for the next interrupt. Right? You clear this interrupt, you wait for the next interrupt. When the next interrupt happens, you skip again. Decrement now from 15, you get 14. The results are still not 0. You go and clear that interrupt here at out, and then you wait for the next interrupt. So this is going to happen 16 times. That 16 interrupts equals to your 1 second according to the calculation. So when I return, when you skip here, you will skip when temp is decremented from 16 up to 0. So when the results are 0, you're going to skip this go to and you're going to return. You return from what? From the call. So a call says jumps there. When you return, you come back from where the call was and you continue under the call. Right. So when we return, that will be exactly 1 second. We will have waited 1 second in that routine. And then after that 1 second, we now have to start initializing our LCD. Right. Now, I'm going to set up my LCD in 16 or in 8-bit mode. Sorry. I need to set up my LCD in 8-bit mode. So to set up your LCD in 8-bit mode, they are saying you need to send 3 times the instruction at 3, it is 3 8. Where is 3 on a higher nibble will be okay. Let's look at this. Let's look at where will 3 be. Let's look at this set of instructions. What can we send here? Where we need to look at DL, N, and F. This is set interface length. You see, the instruction that we need to do is to set interface length, whether it is 8-bit mode or 4-bit mode. So we need to look at DL, N, and F. DL, if that DL is 1, we are using 8-bit mode. If that DL is 0, we are using 4-bit mode, right? Now, and then if the N is 0, we are using a one-line display. If N is 2, we are using, okay, if N is 0, we are using a one-line display. If N is 1, we are using a two-line display, right? And then if F is 1, we are using a 5x10 font. If F is 0, we are using 5x7 font, right? So for this application, we are going to send we are going to use a two-line display, because this is a two-line display. So, and we want a data 8 length. So DL is going to be 1, and then N is going to be 1, because there is a two-line, and then font, we can use the bigger font, 5x10, or we can actually use the smaller font, 5x7. Okay, let's use the smaller font, 5x7. So this is going to be 110. 110 for DL, N, and F. These ones we can always put them as zeros. They don't really matter. The stars one. Right. So now, what will this value be in 8-bit? So this is the first 8-bit. This will be DL is 1. So this is going to be 3 in hexadecimal. And then this is 1 0 0 0. It's going to be 3, and then this is going to be 8. Right? These stars, they don't really matter. We make them zeros. F, we want to use the small font, so we make it 0. But we're using a two-line display. This is going to be a 1. So this is 3 8, which we need to send to the display to set the length and the size if it's a two-line or a single-line display. And now, when we initialize our display, it is written in some applications that we need to send that 3 times. Yeah. This is basically for 8-bit mode. This is done as follows. Before, or this is actually the initialization process. But now this is when they're using a single line display. So instead of 3 8, they will send 3 0. They're using a single line display. You wait for the LCD to warm up. They're saying 15 milliseconds. 1 millisecond will be more than enough in my application. Now you send this instruction 3 times to set the data, the length, data length of your LCD. You send it 3 times, but we will be sending 3 8, not 3 0. We'll be sending 3 8 3 times in our application. Then we can do the rest as we wish, depending on what we want to do. Right. So this I've done already. I've made this 1 second, although they are saying 15 milliseconds. And now in our application is a two-line display, so we're going to send 3 8 3 times. Let's do that in our program. But now remember, this that we are sending, what is here, it's actually instructions, right? It's not data. We are sending instructions to say this is, or we are configuring our LCD in 8-bit mode. It's an instruction. Our RS line must be 0, right? How do you differentiate when you send data and when you send an instruction? Remember, when you send an instruction, RS line becomes 0. When you send data, RS line becomes 1. Right, so because we want to send data, let's make RS line 0. And according to our circuit diagram, our RS line is on port A0. So we need to make A0 low before we start sending that information. To know that we are sending instructions, A0 must be low, right? So now let's do that. Let's do that and say A0 must be low. Let's do that in the program. So we say bit clear file port A RA0 or port A comma 0 will still work. Although there we are switching RA0, we are actually selecting to send command. So I can say send instructions or send command to the LCD. We choose to send a command by clearing that RA0 because that's our RS line. Now, what command do we want to send to the LCD? To the 8 data lines, we need to send that 38. So move literal to W. The instruction which we want to send is 38. And we want to send it to the LCD. But now, that instruction or that data is connected to port B. So we need to send that 38 to port B. We will be sending it to the data lines of the LCD. So we just need to say now, move this 38 into port B. Port B. Now, after we have done that, we are not finished yet. Although we have sent the data to port B, we haven't actually sent the data to the LCD. Right. The data is at the input of the LCD. We need to clock that data in for the LCD to read it. How do we clock that data? We clock it by making use of the E line. The E line, which is A1, must be toggled high and back low to send that information to the LCD. Right. So how are we going to clock that? Basically, what we do is bit set file port A RA1 for a small period of time, and no operation instruction will do. That will be just a 1 microsecond delay, and then we say bit clear file. So we just pulse it. Port A RA1. We have successfully sent information to the display. Now that we have sent this information to the display needs time to process that information, right? And if it's information, it needs to display it. If it's an instruction, it needs to execute that instruction. So how do we now allow it to process that information? We call a delay here. We call a delay, or that delay, it doesn't matter what you want to call it. Let me just call this delay a millisecond delay. So a millisecond with just MSCEC, lowercase. And then I need to define what this millisecond delay is. Just like I defined what that 1 second delay was or is, right? So I'm going to do the same now for the millisecond delay. I said 2 milliseconds will be enough. Forget about a lot of other things. I've done this 1,000,000 times to tell you that 2 milliseconds delay will be enough for these LCDs. So I'm going to create a delay there for 2 milliseconds. So clear file TMR0, and now my millisecond loop will be, it's just a label, that one, don't worry about it. Move file tmr0 into W. There's so many ways you can use timer 0, right? You are not restricted to how you use it. You can use the interrupt, or you can use polling to check what is in the timer 0 register. For this one, I'm going to use polling and check if it has reached the value 7 from 0. The value 7 or 2 milliseconds will be actually 14, which is 0E, right? I'm checking basically what's happening in this program. I'm clearing timer 0 to start at 0, and I want to check if it has counted up to 14. Right. Now, if it has counted up to 14, that will be around 2 milliseconds. Right. So I'm saying now read the value that is in timer 0, subtract 14 from it, 0E from it, and check if the results are 0. If the results are 0, it means I had 14 minus 14. And now, how do I check if the results are 0 of that subtraction? Bit test file skip if set. The status register has what we call the 0 bit. Now, the 0 bit will be set whenever the results of an arithmetic are equals to 0. Whether that arithmetic was add or subtract or any other form of arithmetic available in your microcontroller, if the results of either that arithmetic or the logic operation are 0, the 0 bit will be set, provided that the instruction affects the 0 bit, right? So I know that the subtract affects the 0 bit, and if the results of that subtract are 0, the 0 bit will be set. So I'm checking, is the 0 bit set? If the 0 bit is set, it means now timer 0 has counted up to 14, I can skip. But if the 0 bit is not set, then I don't skip, because that timer 0 hasn't reached 14. Where do I go? I need to go and read it again to check if it is 14 now. So go to read it again. Check if it has reached 14. Go read it again, subtract 14 from it. Has it reached 14? Is the result of the subtraction 0? If it is 0, skip, it has reached 14. And counting from 0 to 14 in timer 0 set to the prescale of 1 to 56 using 4 megahertz, that will give you 2 milliseconds. And then you return from that, and then it means here I must have used call that milliseconds, and then here it's actually wait 2 milliseconds. Right. Now I've sent that instruction. This instruction, I need to send it 3 times. So I can just copy this and print it 3 times. Print that. There. Okay. And then print it again there. So I'm sending this 3 times as it is instructed on the data sheet that you need to send that 3 times when you set up your microcontroller, when you initialize your microcontroller. You need to send it 3 times. But now, remember, because this is our 2-line display, we are sending it 38 instead of 30. We send it 3 times. Now, there's an issue here. Okay, I am the one who has an issue with this. You see, I've done this code, exact same code, 3 times. This is not efficient for a programmer. There's a way that we can try and minimize duplicating the code, more especially this part. So what I'm going to do is I'm going to create this and make it a routine, single routine. So I'm going to cut this. See this is a process that repeats. So what am I going to do instead of writing this whole process again? I'm going to call it. So I'm going to say call send, right? So we actually send to LCD. Let me just call it send to LCD. Now, what will send to LCD be? copy that, and then send to LCD will become this whole routine. This part will be sending to LCD up until I wait, and then I have to return. Because I'm calling it, I have to return. And then this becomes a subroutine. This whole part becomes a subroutine. Right. Now, instead of having to write this thing all over again, I'm just going to call it for all of this. Paste there. So this will be call send to LCD. This will be call send to LCD. And now this is a subroutine. I must move it. Let me move it under my 1 second delay. 2 milliseconds delay, sorry. Now I'm moving 8, sending to LCD, move 38, send it to LCD, move 38, send it to LCD. 3 times. This routine, instead of doing it the same routine 3 times, I've just made it a subroutine, and then it minimizes my code. Remember, I'm still sending a command because the RA0 it is still cleared as I send this data. Right, I've sent that 3 times. Now the next thing I want to send, let's say according to the flowchart. According to the flowchart, the next thing that I want to send is what I've sent now is 8-bit mode, right? I've set my LCD in 8-bit mode. I need to tell my LCD now to increment cursor every time I send an instruction or I send data to it. I need to inform it that it needs to increment its cursor every time, or its address every time I send data to it. Now, I know that instruction is actually 06. Let's see where it comes from. Here, let's look at this one. Set cursor move direction. Set cursor move direction. That's what we need to look at. So we need to look at ID and S, right? Let's look at ID and S. We know that D2 is 1, the rest are zeros, and then we need to look at ID and S, and then we get an 8-bit value which will inform or instruct our microcontroller to increment the cursor whenever we send data to it. So we need to look at ID and S. So ID says increment cursor after each byte written to the display. The S is shift display when we don't want to shift the display, right? We want to increment, right? So we'll make ID 1, but S will make it 0, right? So if we make ID 1, we make S 0. This in hexadecimal becomes 06. That's what we need to send now to the LCD, right? So we go into our program. It is still an instruction. So RA0 it is still cleared. RA0 it is still cleared. So we say move a value, literal value 06 into W, and then let's call our send to LCD. We're gonna send that information to the LCD. This will have informed our LCD to increment the cursor whenever we send a new data to it. Right. So this is basically set up LCD in 8-bit mode, and this must be sent 3 times. This must be sent 3 times. Now, I have done initializing my LCD. I want to now start writing data to it. Right. According to the flowchart, I'm done initializing now my LCD. I now want to write to that LCD. Let's see now, how can I write to that LCD? Now, let's start off by saying Let me clear the LCD. When you clear your LCD, basically is going to start writing from the very first pin, the very first location, the top right, the top left corner of your display. It will start writing from there, which is address 80. These places where you can write, they have addresses. The top line starts at address 80 in hexadecimal, and then the second line starts at address C0. So you have 80 up to 8F because it's a 16 by 2. So the first line starts at 80 up to 8F. That's 16 characters you can display there. And now the second line starts at C0 to CF. Those are addresses which we can jump to. Let's say if you want to start clearing the LCD, then the default address will be 80. It will start writing at 80. Or you can instruct it to jump to any other address between 80 and 8F and between C0 and CF. Right. Now, yeah, this is 80 here up to 8F. This will be C0 here up to CF on the second line. So let's say if you don't want to clear, or let's just start by clearing the LCD. Move a literal value into W. Now the value to clear your LCD according to our data sheet is this one, 01 in hexadecimal. We want to clear the LCD. There's an instruction you send. So let's send that instruction where you now clear your LCD. So 01 must be sent to LCD. Send to LCD. Right? Now here will be clearing the display. Clear your display, right? Now, let's start now writing to your LCD. In the main program, I will start by saying, let's jump to the first address. We are already there because every time you clear your LCD, you actually on default jump into that address. But let's jump to that address. I said the first line, the address of the first line and first character on the LCD is address 80. So first line and first address of that line. First line, first address of that line is at address 80. We send it also as a command because we're instructing the LCD to jump to that address. So we call send to LCD. Right. But now at that address, what is it that we want to write? Let's say you want to write your name. Let's write mine there. So I will send characters. But now before I send characters, I need to inform the LCD now. Now I'm sending data. I'm no longer sending instructions. So data, I need to send it by, or set it by setting port ARA0. It means now I'm sending data now, no longer sending commands. Send data to LCD. Now, move literal value into W. There are two ways you can get the information. Let's say, in my case, I want to display my surname, which is written PHALI, right? Now, I need to start first by sending P, and then I'm going to send H, A, L, and I, right? In assembly language, unfortunately, this is dealt with character by character. In most of programming languages, you send this as a string and then it gets displayed miraculously. But in assembly language, it is done step by step, character by character. Now, how do I get the character P or the data or the hex value that represents character P? It is either I refer to this ASCII table and say for P, an uppercase P will be 5 in hexadecimal. This is the upper bit. 50 will be my P, right? So I'll say 50 in hexadecimal is what I have to send now. So I'll say 0x50. So this will be send the character P, right? Call the same routine, send to LCD. But now the difference is I'm sending to the LCD with port A0 set, indicating now this is data to be displayed on the LCD. Is no longer an instruction, right? But I'm still using the same send routine, right? That is one way I can send a P, getting its ASCII code from the ASCII table and sending it to the LCD. Or let me just leave P like that. Go to the next one. Move a value into W. Remember now, the name that I want to display is PALI, P-H-A-L-I, PADI, actually. Now, I need to send an H now. I've sent P. I can either go to the table and look for a character H. Where will H be? And then H will be represented by uppercase H will be represented by 4 and 8 in hexadecimal. So 4, 8 in hexadecimal is H. Okay, let me do the P this way as well. So in hexadecimal, 4, 8 will represent my H. So send character H to the LCD. So I'm going to call send to LCD. Right. Now I want to send the next character, which is A. Move literal to W. Now instead of going to look up for A, I'm just going to do it this way. Now this will be send character A. Now when you do it this way, the compiler will automatically get the ASCII code for this character. I could have done the same thing for H, for P. Instead of looking at the ASCII table, you can just make use of this. So I'm going to do that for the rest of the remaining characters. Call send to LCD. And then this will apply to LI as well. So this will be D send to the LCD. Right. Let's say for now, after doing this, I want to remain in an else loop. Go to loop, and then this denotes the end of my program. Let's see if all is good. And let's see if I haven't actually made mistakes. Let me try and build that. Doesn't look like I have any mistakes. Then I can try and simulate this program. Let me try and get the simulator up and running. Okay, I have the PIC simulator. Need to select the PIC 16F84A. I want to view the microcontroller. So this is my PIC 16F84A. Tools, the LCD. There's LCD here. LCD, right? And now this LCD, I need to connect it the same way. So this is a 2x16 LCD. Data lines are on port B. This is 8-bit mode, not 4-bit mode. So I'm using 8-bit mode. My RS line, it is port A0, right? My E line is port A1, right? Is that the case? Let me look at the schematic. Let me look at the schematic. RS line is A0, E line is A1. That's correct. Okay. And now let me then go back to the LCD setup. And then on the LCD setup, LCD is 2x16, data lines are on port B. This is 8-bit mode. RS line is A0, E line is A1. The read or write not used, always connected to ground. Right, that is fine. That is how I want to set up my LCD. And then let's now load the hex file. It is on the desktop under example programs, LCD. Let's load this hex file. Ultimate, let's start. There's a 1-second delay, so it's basically going to take some time before you start. You will see the instructions, the data will start running there, and then there you go. You have PALI displayed on your LCD display. Right. You can add more to the program, do some modifications if you want. Let's say now you want to add the name on the second line. It is my surname on the first line. Let me just add my name on the second line. So now I want to jump to the second line. Need to send an instruction. Bit clear file. Port A, RA0. Remember, RA0 is the RS line for selecting whether you send data or command. So I want to send a command. I clear that line. And now the command that I want to send is the address of the second line, which is C0. 0xC0. And then call send to LCD. Right. Now here I'm jumping to the second line. Go to second line of the LCD, the first address. The very first address of the second line, that's where we're going to. Now here I want to display my name, right? So after going to that second address, now I want to send the name. The name is data. I need to send data. So to send data, that RA0 must be set. So bit set file, port A, RA0. Now send data. We're going to send data. Now I now need to send my name. First character is T. Call send to LCD. And then this will repeat depending on the character that you want to send. Send character T. This is what I'm doing here. And now the actual full name will be Tebang. written like that. So the next character to be sent is E. Right, so here we send E and so on. T, E, B, A, N, G. Right, and now save, build this. Let's stop the current simulation, load the new updated text file, start simulation, wait for a second for LCD to warm up, and then start sending information, end up displaying all that must be on that LCD drive. So you can jump to addresses and send information to addresses. You can shift the display left and right. That depends on what is it that you want to do, and with the help of the information available on the LCD. So this is whether you want to move or you want to shift. This is where the S is. You want to shift to the right or shift to the left, and so on. Now, this is using the LCD in 8-bit mode. Let's do the 4-bit mode. Now, when we use an LCD in 4-bit mode, what does that mean? Now, in 4-bit mode, for our LCD to work in 4-bit mode, basically what it means is that we are only going to use the 4 data lines. And in 4-bit mode, you actually use D4 to D7 of the LCD. You use D4 to D7. Now, this helps you that instead of using 8 bits on your PIC microcontroller, you get to save 4 of them. Let's say maybe in your applications you need extra pins to do controls on other things. You will have 4 data lines freed for your use for other purposes. And then you will interface the LCD only with the 4 data lines, being data line 4 up to data line 7. Now, you still need to send an 8-bit data to the LCD, but using only 4 pins. How are you supposed to do that? You need to now take this 8-bit value and cut it into 2 pieces. The first 4-bit of the 8-bit value, the upper 4-bit. So basically, let's say your 8-bit number that you're supposed to send is clear the LCD, which is 0000001. Right. Let's say now the number that you want to send to your LCD, it is 0000 for the upper bit, and then it is 0001 for the lower bit. It is still an 8-bit value, but you have only 4 pins available to send to it. So how are you going to send this 8-bit value only using 4 data lines? What you need to do is you will say, I'm going to send the first 4 upper bits. I'm going to send the first 4 upper bits here on these data lines, and then clock that information. Clock it. After sending the first 4, get rid of them, send the next 4 on the very same data lines and clock it. So after clocking the 2 4-bit numbers, you wait for the LCD to process that information. It means it takes 2 cycles now to send in 4-bit mode than it takes because it takes 1 cycle to send in 8-bit mode. In 4-bit mode, you have to actually divide your data into 4 bits and send them twice. Send the upper 4-bit and send the lower 4-bit. Right. So that's what happens in 4-bit mode. How do we make use of 4-bit mode? And it actually has to do with initializing as well. That's where when we initialized our LCD, in the first case, when we initialized it, we had to initialize it and tell it that we are using it in 8-bit mode, right? We had to tell it that we're using it in 8-bit mode. To use it in 4-bit mode, we do the same. But now in 4-bit mode, this is still going to be the same. We're just going to change this to 4-bit mode. And now we are going to modify our program to accommodate 4-bit mode, right? So let's go to the program. It's going to stay the same. It's just that we need to change the way we are sending information. And when we send information in 4-bit mode, there's something that you need to be aware of in terms of when you initialize your LCD. In 4-bit mode, when we initialize our LCD, we are still going to send this 3 times as it is, right? So we're going to send that 3 times, as if we are configuring our LCD in 8-bit mode. And now, after sending this 3 times, we need to now change and switch to 4-bit mode. But what value do we send to configure now our LCD in 4-bit mode? It goes back to here to say set interface length. What must be DL, N, and F to set our LCD in 4-bit mode? So we look at, let's say the font, we still want it as the small font, but the DL and the N, let's look at the DL and the N. Set data length. If we want 4-bit mode, this will be a 0. Remember, currently it is still 1 because we want 8-bit mode. But if we make it 0, and now this is still a 2-line display, so this will remain 1. So only DL will change to 0. If DL changes to 0, so this value is going to be in hexadecimal. This is 3 because this is going to be 0. It's actually, DL is our, this is going to be 2. 0, 0, 1, 0. DL becomes 0 for 4-bit mode. This becomes 2. This is still a 2-line display, so this is still 1. We want the small font. These are all zeros. So it's going to be 2, 8 instead of 3, 8 because this DL has changed from 1 to 0, making this 4 upper bits a 2, and these ones will remain 8. So we need now to send 2, 8 to the LCD. But we're not going to change this 3, 8 to 2, 8. We still need to send 3, 8 3 times, and then we change that 3, 8. After sending it 3 times, we change it to 2, 8. Right. We change it to 2, 8. We change it to 2, 8. 2, 8. We send this 2, 8 twice to ensure that we have configured our LC in 4-bit mode. Right. Now this is 4-bit mode, 4-bit mode. But this routine, it is still an 8-bit mode routine. We are not sending this data twice. We are still clocking it once as if it's an 8-bit. We are not sending it twice. How are we supposed to send this data in blocks of 4? So basically, let's start with 8. We want to send 3 first, and then we send 8 after. When in 4-bit mode, we send the upper bit first, and we send the lower bit after. But now we must also bear in mind that in 4-bit mode, only 4 data lines are used. So which data lines are connected to our port B and which port B pins? So we say D4 to D7 of your LCD. Your D4 to D7 of the LCD will be connected to B4 to B7 of the PIC microcontroller. Right. Now, once we have it like that, the data lines D4 to D7 connected to B4 and B7 of the PIC microcontroller. We are going to use this B4 to B7 to send the data. So we need to send the upper bits first, the most significant bits first. So when we send 3, 8, we need to send 3 first, then we send 8 later. So let's move this 3, 8 into W, and then we call a routine that says send to LCD. But now this routine cannot send that as if it's one 8-bit value. We want to send, okay, the first upper 4 bits, right? But let's, for now, move W to file. I'm going to say temp, because we already have a register called temp. Let's move whatever the value which we move into W before we call. Let's temporarily save it in the temp register, and then we can start writing maybe the first upper 4 bits. Right. Send the first upper 4 bits to port B because they are already aligned. B4 to B7 will be having the first upper 4 bits sent to them. Clock that data. You don't have to call a millisecond here. You need to call a millisecond once you have sent the second bit, 4 bits. So to do that, we are going to say swap file. What is in temp? Swap it around. Make the lower bits now upper bits, and make the upper bits the lower bits. Swap them around. Move that to port B, and then clock it again. And then once you have clocked it for the second time, and now this second time you are clocking the lower 4 bits, wait that 2 milliseconds for the display to process that information. Right, and then the rest will remain the same. The rest will remain the same. Let's now look at how you will set up your PIC microcontroller and its. Let's stop this simulation setup. Our interface is no longer 8-bit mode, but it's 4-bit mode. The higher 4 bits of port B, because port B is our data line, the higher 4 bit, meaning we're using B4 to B7. We could have decided to use the lower bits, B0 to B3. We can either decide to use the lower bits or the upper bits. I've used the high bits. So let's use it 4-bit mode in the upper bit of port B. The RS and the E line are still the same. RW is still not used. Let's keep that as it is. Before I load the hex file, did I build it? Let me build the program. And then once it's completed, let us load the hex file and then start simulation. Wait 1 second. Start sending information to the LCD. Still displaying the same thing. Still displaying the same thing. So that's the difference between 8-bit mode and 4-bit mode. And now in 4-bit mode, what is most important is that you send your information twice, because it is actually still 8-bit but sent in chunks of 4 bits. So you first the first upper 4 bits and then you send the next lower 4 bits. Meaning in 4-bit mode you send data twice, in 8-bit mode you send it once. Now remember, when you send data, you're actually using the E line to clock that data, right? So you send data to your port and then you clock it. In 8-bit mode, you need to clock once, the whole 8-bit will be sent. But in 4-bit mode, you need to send the first upper 4 bits, clock them, and then send the second lower 4 bits, clock them for the whole 8-bit to be sent to your display, right? That's basically an LCD and PIC microcontroller in assembly language. I hope this helps some of you who are using or intending to use assembly language in your application or in your studies, and enjoy your assembly language. Thank you, guys.